Pythagorean Theorem. It's everybody's favorite theorem, right? The Pythagorean Theorem. And what we're going to do, okay, so first of all, the Pythagorean Theorem, right, the way we know it, works for right triangles only, all right? So in a right triangle, right, what is the Pythagorean Theorem? A squared plus B squared is equal to C squared. And so how do you know which of those letters is which one?
C is the hypotenuse and A and B are the legs.
Okay, so C is the hypotenuse, okay, and A and B are the legs, correct? So this is a leg, this is a leg, this is the hypotenuse. And how do we know it's the hypotenuse? Because it's opposite to the what? The right angle. Okay, good. Right, it is the longest side. And we know that A squared plus B squared is equal to C squared. Okay, now, so let's talk about where this comes from and how we can prove it, right? We're not going to do a two-column proof for this one. We can do a two-column proof, right? But we're going to we're going to do it. We're going to prove this using geometric mean, which we learned in section 1. Okay, and it's actually like a pretty cool way of doing it. So look at what you have here. You've got a triangle, right? A right triangle, this large triangle here, triangle A, B, C. And the way we label sides of a triangle, if this is angle A, we give it a capital letter, right? And then the side opposite to it is little a. And then the side opposite to capital B is little b, and so on. So what we have here is this large triangle with the altitude drawn. Does that remind you of the problems you had in the last lesson? Right? Yeah. So in the last lesson, we learned about a couple of proportions that go with this, right? One was this loop that I told you. Y over H is H over X. You guys remember that one? Okay, good, because we're not going to use that one. Another one that we learned, right, was with the hypotenuse on the leg. Remember? So let's write that one. So the hypotenuse here, I know it says C, but I'm going to use Y and X. Just stick with me. Okay, so Y plus X, that's the whole hypotenuse, over one of the legs, let's say A, is equal to A over what? Y. That's one, okay? Another one we can get from this is like with the B, right? So Y plus X over B is equal to B over X, correct? Now, you know what we're going to do here? We're going to cross multiply. Okay, so from the first one, I get that A squared is equal to Y squared plus XY when I distribute. And for the other one, I get B squared is equal to how much? Right. XY plus X squared. Okay? All right. So, guess what I'm going to do right now? I'm going to add these two. Okay, so I'm going to add these two. All right, so here's what I'm going to do. I'm going to write them here. A squared is equal to, I'm going to write it like this. XY plus Y squared. B squared is equal to XY plus X squared. Okay? Now I'm going to add them. When you add them, on the left side, you get A squared plus B squared. Write these down. A squared plus B squared is equal to, what do I get here? XY plus Y squared plus XY plus X squared. Don't combine them. Just write them like that for now. Okay. Now, guess what I'm going to do? So this is A squared plus B squared is equal to. This one, I'm going to factor by grouping. Remember how to factor by grouping? You split it down the middle, from the left-hand side, what can I factor out from these two terms? A y, and I get x plus y, correct? What can I factor out from here? An x, and I get y plus x. Now, look at how factoring by grouping works. And by the way, if you forgot how to factor by grouping, which I learned it in Algebra 1, and then, somehow when I was doing factoring again in Algebra 2, I realized I had forgotten it. It's okay. It's not a big deal. Your life's not going to end. You're going to relearn it again in Algebra 2. We're only going to use it for this proof right here, okay? So the way this works is, do you see how you have an x plus y and a y plus x? Do you see how those are the same term? Whatever the same term is, you just write it here, okay? And then what have you got left? Y plus x, okay? That's what you have on the outside. Oh, I'm sorry. Wait, I'm sorry. I forgot the plus. The plus has to stay. Y plus x. Okay? Now, what do we have here? A squared plus b squared. Look at what I have. X plus y plus another x plus y. So how many x plus y's do we have? 2x plus y's. Wait a minute. What did I do here? One second, sorry. Sorry, give me 1 second, hang on. So you see how this x plus y is the same, right? You write it off here, x plus y, and then the other one is times, sorry, I had it right before and I confused myself, times y plus x. Okay? So what do I have here? X plus y times another x plus y. Now let's go back to the diagram. How much is x plus y? C. So this is c times c. So finally, a squared plus b squared is equal to what? C squared. Okay?
Wow.
Yeah.
That was a lot.
You just did a proof. You just did a mathematical proof. It is a lot. So, I want you to know where these things come from, because you should know, right, that these things do come from somewhere. They don't just fall into some mathematician's lap when they were like sitting around after dinner, right? So they come from somewhere, and in our honors classes, it's not about the what, it's about the why, right? Where do things come from? Why are they things the way they are? So, I want you to know this stuff. You don't need it like explicitly for a test or a quiz, I might ask you like how to prove it on a bonus question or something, right? But you should know like, how these processes come to be, okay? All right. So let's move on. Let's use the Pythagorean theorem. Okay, so go ahead and take out your calculators too. Okay. Let's do this. So find the value of x. This is a right triangle, and you have the legs as 20 and 37.5. So this will be 20 squared plus 37.5 squared is equal to x squared. When you plug this into your calculator, that should give you 1,806.25 equals x squared. Now, here's the deal. Take a square root, take a square root. Especially when you've got decimals like this, you're not going to be asked to do that by hand, okay? So this is going to be x is 42.5. So for this one, you're going to use the calculator. Okay, for this one, we're going to do it without a calculator. So let's do that, no calculator. Okay, so here we go. The legs are x and 4 over 7. So x squared plus 4 over 7 squared is equal to 5 over 7 squared. Now we take a breath because we're going to do this slowly. X squared plus, when you square the 4 over 7, what do you get? 16 over 49 equals, you square the top and you square the bottom. This 2 belongs to both of them. 25 over 49. Now, when you subtract, okay, minus 16 over 49 minus 16 over 49, x squared is equal to 9 over 49. Now, when I take a square root, just like when I square top and bottom. When I take a square root, I also take a square root of the top and the bottom. So 3 over 7. In the background, when you take a square root of a fraction, it's really root 9 over root 49. So you can do it separately. Okay? Okay. Now, converse, because every theorem must have a converse, right? Okay, so the Pythagorean theorem said if you have a right triangle, then the square of the legs equals the square of the hypotenuse. The converse says if you have a triangle and a squared plus b squared is the same as c squared, then the triangle is what type of triangle? A right triangle. Okay, so it just goes backwards. So if a squared plus b squared equals c squared, then triangle ABC is a right triangle. Okay, so let's see if PQR is a right triangle. Without the right angle anywhere, how do you know which one C is? Yeah. It's got to be the largest side, right? So 5, 6. How much is root 61?
About 8.
Well, okay, right. So root 49 is 7, right? Well, this must be bigger because it's root 61. If it's a calculator okay part, you can plug it into your calculator and you know that it's like 7.8 or whatever, right? Okay. So this is C because it's the largest. The other one are A and B, and we don't care which one is A, we don't care which one is B. So 5 squared plus 6 squared, is this equal to root 61 squared? I don't let the root bother me because it's a squared plus b squared equals c squared. I take a as is, square it, b as is, square it, c as is, square it. Hang on. I write it up with the squares first, then I worry about how am I going to square this number. So 25 plus 36, what is that one? 61, because the square and the square root cancel each other. And question mark, is it equal to? So here, this gives me 61. That does equal 61, so yes. Questions? Okay, next. Okay, root 11. Okay. What's the closest root you know? Like perfect square. Root 9 is 3. Root 16 is 4. So this should be between 3 and 4. Okay? Or if you're doing your homework, plug it into your calculator and you'll see that it's not bigger than 7. So what's C here? 7. Okay. So A squared. I don't worry about what I'm going to do. I just write it first. Plus B squared equal to C squared. Whoops, that's a 5 squared. Okay? And with a question mark, because I don't know if it equals. Okay? It's not? 11 plus 16. Does that equal 49? I'm sorry, 25.
No, it's not.
It's still not. Okay? 36 is, okay, so this is how we write it. 36 is not equal to 49, so no. Okay?
We're gonna do the same thing.
Oh my goodness. And I don't even, like, I don't know if that, like, if it's a good thing or a bad thing that it's not a Pythagorean, you know, that it's not a right triangle, but, you know.
I like these problems.
Yeah, same. I love the Pythagorean theorem.
They're probably gonna get harder though.
But,
They're probably gonna get harder though.
Oh.
I'm not.
You say that like we're in an honors class or something.
I turned the page and
Okay, Pythagorean triples. I love Pythagorean triples.
That sounds so odd.
Pythagorean triples are, a Pythagorean triple is a set of 3 whole numbers that make a right triangle. So for example, look at this. 5, 6, and root 61 made a right triangle, correct? So those 3 numbers satisfy the Pythagorean theorem. Are all 3 of those numbers whole numbers? No, so they're not Pythagorean triples. All right? Well, what's an example of a Pythagorean triple? Well, this is the most famous one. 3, 4, 5 is a Pythagorean triple. Because if these were sides of a triangle, right? Which one would be C? 5 would be C. And if you applied the Pythagorean theorem, 3 squared plus 4 squared, does it equal to 5 squared?
Yeah.
You know what? It does. Because these are 3 whole numbers that satisfy the Pythagorean theorem, so these are 3 whole numbers that make a right triangle, it's called a Pythagorean triple. There are others. Huh? They're not what? Yeah, they're not whole numbers. Right. Well, it's not. So the question for here says, you're like fast forwarding and stealing my thunder. So the question here says, determine first whether each can be measures of a right triangle, like we did here. If so, is it now also a Pythagorean triple? Okay? Okay. So, between the 8, the 15, and the 16, which one would qualify as C? 16. So, 8 squared plus 15 squared, is this equal to 16 squared? Okay, so here we go. 8 squared is? Okay. Now, what's 15 squared? 225. So this is the chapter where, you know, little by little you'll get used to these, and we'll try to practice as much as we can. 15 squared is 225. 16 squared is 256. They're not equal to each other. So we can just say they are not equal. So this is not a right triangle. Okay? Ooh, what about the next one? Okay, so which one would be a Pythagorean triple here? I'm sorry, which one would be C here? So if you're not sure, go ahead and plug it into the calculator, right? Like root 3 over 5, root 6 over 5. Let me show you a trick though. Okay, all of these have the same denominator, right? So we can compare the numerators. Look at the root 3 and the 3. Root 3 is smaller, so I know root 3 over 5 is a smaller fraction. So here C is going to be 3 over 5. So here's what we're going to do. Again, don't let these scare you. Just write it down first. A squared plus B squared, is this equal to C squared? Okay? Then you worry about the squaring. This exponent belongs to the root 3 and the 5. So that gives me 3 over 25. What does the second one give me? 6 over 25. Does this equal 9 over 25? Yes, it does. So, this is a right triangle. Is it a Pythagorean triple? Are they all whole numbers? No, not a Pythagorean triple. Okay, next. All right, go ahead with your calculators. Do the next one. On your mark, get set, go. I'll pause this for a minute. So right triangle and Pythagorean triple. Okay, the other one, root 2 over 7 squared plus root 3 over 7 squared. Is this equal to root 5 over 7 squared? So 4 over 7, 3 over 7. Yes? I'm sorry, 49. Huh? Oh my God. Now I'm rushing. So 5 over 49. I did what I tell my children to not do, which is like if you rush, it makes you go slower because then you make all these mistakes and you have to do it twice. And that's exactly what happened to me. I wasted more time. So this is a right triangle. Is it a Pythagorean triple? No. Okay, so here's the deal about Pythagorean triples. So they come up all the time, and it's very important for us to recognize them. It saves a lot of work, first of all. It helps also. So suppose 3, 4, 5, I mean, not suppose. 3, 4, 5 is a Pythagorean triple, right? So are all of its multiples. So for example, 3, 4, 5 is a Pythagorean triple. And if you multiply all three of those by 2, 6, 8, 10, also Pythagorean triple. If you multiply by 3, 9, 12, 15, also a Pythagorean triple. Another famous Pythagorean triple is 5, 12, and 13. Okay? Why not?
But like, how does it get famous?
Pythagoras said so, huh?
How does it get famous?
Who? Pythagoras?
No.
The Pythagorean triple? Well, because it is like a subset. It's like those special whole numbers, right? And they have all those characteristics. Okay, let's do some more. Pythagorean inequality theorems. Okay, so for this one, it helps, if we write the Pythagorean theorem like this: c squared is equal to a squared plus b squared. Okay? Just in, the c squared first. And what we want to do is we want to compare the c squared to the a squared plus b squared. But the one thing that students always forget, and this is the only place where the mistakes come in, is they forget to write it as c squared first. Okay? Because the Pythagorean theorem is, like we're so used to seeing it as a squared plus b squared equals c squared. For this one, you have to write it as c squared first. So here's the theorem. It's very straightforward. If c squared is less than a squared plus b squared, then what you have is an acute triangle. If c squared is greater, then it's obtuse. Okay? So if c squared is less, acute. Equal, right. Greater, obtuse. Okay? So c is always the larger one. Okay? So determine. Okay, so look at this example. This set of instructions. Determine whether each set of numbers can be the measures of the sides of a triangle. So first of all, we're going way back. First and foremost, is this even a triangle? And then, is it acute, obtuse, or right? How did we tell if, given three sides, if there were sides of a triangle?
The smaller sides are bigger than the larger sides.
Correct. So this means a plus b must be greater than c. So this one, 3 plus 5 is less than 9, so it's not even a triangle. Okay? For that one. Because if it's not even a triangle, then who cares if it's acute or obtuse? It can't be any of them, right? What about the next one? Is this a triangle? Yes, this is a triangle. So now, which one is C? The 15. Must write that one first. So 15 squared. And then I like to leave like a little blank here for the sign to go in. 9 squared plus 12 squared. 15 squared is 225. 81 plus 144. So this is 225. 225, so what sign should go in there? Equal to, so this is a right triangle. Okay? Now, do the next two. They both work as triangles. Figure out what C is, and then compare it to A squared plus B squared. Okay, so this one is greater than, and it is obtuse, and the first one was acute. Okay, so before we stop for the day, let's do some perfect squares.